Yeah, good morning, all. Welcome to the 1 week Atal at FDP program. The dignitaries are will join in few minutes. Hope my audio and video. Hope my audio is clear.
Yes, sir.
The person you call.
Welcome, Arun Tiwari sir.
Hello. Good morning, sir. Sir, welcome to the inaugural. We are just waiting for the principal to join in a couple of minutes. Sir, your audio is not heard.
Please unmute your mics. Okay.
Yeah. Can you hear me now?
Yes, sir. Yes, sir. Perfect.
Namaskar.
Namaste, sir.
Nice to see you after a very long time.
Yes, sir. Thank you so much.
Good.
One
So
minute.
I'm online. You focus on principle.
Sure,
Okay?
sir. Sure, sir. Thank you.
Thank you.
Sir, good morning, sir. Principal, sir. Welcome to
Yeah,
the
good
inaugural
morning.
session, sir. Yes,
Yeah,
sir.
yeah, good
We'll
morning,
start.
good morning,
We'll
madam.
start. We'll start, sir.
Okay.
Husna, you can start.
Okay, ma'am.
Yeah.
Am I audible, ma'am?
Yeah, perfect.
A very good morning to one and all. This is me, Husna, and it gives me immense pleasure to welcome you all to the online inaugural function of the 1 week online faculty development program on 3D printing and design, sponsored by AICTE Training and Learning Academy, which is being conducted from the 8th to the 12th of November. 3D printing is one of the most important technological advancement in additive manufacturing, which has been implemented and recognized as a part of modern industry, as it has many advantages over conventional approaches. In today's world, the applications of 3D printing are very useful for research and development of various components, ranging from simple structures used in everyday life to complicated components used in different industries. This program is thus designed for a better understanding about what 3D printing is, the different techniques involved in it, and its wide range of applications. Gracing us with his presence, our chief guest for today is Dr. Arun K. Tiwari. He served as a missile scientist in DRDO, significantly contributing to India's military missile development effort. He was also a member of the advisory team to the President of India, Dr. APJ Abdul Kalam. Apart from this, he is an articulate writer who has written several books and co authored 5 books with Dr. APJ Abdul Kalam. He currently teaches at the School of Management Sciences, University of Hyderabad as an adjunct professor, and is also the secretary of CARE Foundation and the Platinum Jubilee Mentor of CSIR IICT. We also have with us Principal, College of Engineering, Osmania University, Professor Sriram Venkatesh. He's got 26 years of experience in teaching. He's been the director for product design, development, and additive manufacturing, Osmania University, since 2009. He has published about 110 papers in various international and national journals and conferences. He's also got a rich experience in many research and consultancy projects in 3D printing. I welcome you all, sir, to this training program. Now, I request Professor Suman, Head of BME Department, Osmania University, to give the welcome address.
Thank you, Husna. Am I audible, Husna? Hello?
Suman, sir?
Yeah, Husna. Hello?
Your audio is very low.
Hello?
Hello. Yeah, Husna. Sorry for the delay. There is some technical error. So, very good morning to all the members. Respected chief guest, Professor Arun K. Tiwari, the president of the event, Professor Sriram Venkatesh sir, the principal of the University College of Engineering, Professor M. Malni, the coordinator of the Atal FDP program, and all the faculty members, staff, and all the members who are attending this event from different parts of the country. I welcome you all for this 1 week Atal FDP sponsored by AICT on 3D printing and its applications. before I discuss about the event, I'll just briefly give an introduction to the biomedical engineering department, because most of the members are from different parts of the country. To tell about the department, the biomedical engineering department was started way back in the year 1982. In fact, it is the first university, Usmania University is the first university to start the biomedical engineering course at the undergraduate level. And we have started this course in the year 1982 with an intake of 10 students. And later, the strength was increased to 30 in the year 1993, and we have a separate department status in the year 1996. And in fact, we have even started the PG program in biomedical electronics in the year 2006. Currently, we are also offering the PhD program in biomedical engineering, both in part-time as well as in full-time. And currently, we have about 12 students who are pursuing their PhD program. And the department has received various research grants from DST, UGC, and in fact, we are also one of the members of the UP University with Potential for Excellence, which was awarded the status to the Usmania University. Biomedical engineering department was also one of the active member of that particular UP status of the Usmania University. And our BE program, Bachelor of Engineering in Biomedical Engineering program, has been accredited by National Board of Accreditation for 6 years with effect from 2019. In fact, among all the departments of the University College of Engineering, Biomedical Engineering department has got 6 years. And we have a biomedical instrumentation center that was established in the year 1994, which caters to the calibration and maintenance, troubleshooting of the medical equipment in hospitals. During this COVID-19 period, we have extended our service to various hospitals. In fact, some of the agencies who are manufacturing ventilators, we assisted them for calibration, as well as we have assisted T-Works as well as Meda Servo Drives, who have developed ventilators, and we assisted them in the quality assurance of the ventilators. So in fact, it is a proud moment, and due to this COVID-19 pandemic, we are having this program in online. And this particular program, Atal FDP was sponsored to ASCTE, and we planned the lectures from both academia as well as from the industry persons. I wish that the keynote address, which would be given by our Professor Arun K. Tiwari, he has vast experience in different fields, not only in mechanical. He, in fact, one of the stent he actually designed with Dr. Kalam, Dr. APJ Abdul Kalam, which is a well-known thing, Kalam Raju stent. So his keynote address will add value to this particular course. And among the other guests, our guest of honor, Professor Sriram Venkatesh sir, in fact, he is a pioneer and he is a very good researcher in this particular field, 3D printing. In fact, he is the first person to establish this rapid prototyping center in the Usmania University. In fact, it is of a state-of-the-art technology which we have in our University College of Engineering. His experience would definitely give a much-needed trust and much-needed exposure to all the participants. I wish that all the participants will gain sufficient knowledge which will be useful for their academia as well as research. I wish all the members to have a fruitful sessions and fruitful enriched knowledge in the coming 5 days. Thank you. I wish all the best for the coordinator as well as the event organizer. Thank you.
Thank you, sir. Now I request Professor M. Malini, the course coordinator, to brief us about the ATIL AICT course on 3D printing and design. Ma'am.
Yeah, good morning, everyone. Respected Professor Arun K. Tiwari sir, Professor Sriram Venkatesh sir, Dr. Suman, and all the participants and my dear colleagues. Yeah, it is a proud moment for me to be the coordinator of this particular Atal FDP program. And as Husna has already given the importance of
Ma'am, you're not audible, ma'am.
Yeah, 3D printing is not new as we think, but it has started way back in 1980s. But the impetus given is in the recent few years, especially with the its applications in medical field. We are having its impact really seen. And among the speakers of the FDP this week, we also have two doctors who are actually using 3D printing in their regular work daily routine. Also, we have a few experts drawn from industry who are the actual CEOs of a company, iMake, and also Anatomize 3D. So we have these persons who will be giving us lectures because they are in the field. And we also have few experts drawn from academia who will be giving different applications of 3D printing. And coming to this particular Atal program, as you all know, AICT is mainly committed to the development of quality technical education, and and this FDP, Atal FDP, is an initiative of AICTE to actually train the trainers. So it is aimed at training the faculty so that they can train the students. As we all know, especially in India, we have so many unemployed youth, and if we look for any job to be done, we don't find the required people. So in order to bridge the gap, we are going to focus on skill development. So if we can provide the necessary skills, so this is going to definitely bridge the gap between these two aspects. So this is a very good initiative by the AICTE, and we also have the participants from a variety of backgrounds. So I am sure the participants are going to gain some knowledge, and definitely it is going to be useful for their research work. And we have an illustrious chief guest with us, as Suman has already told, with a rich experience in a variety of fields. So he is going to give us some key directions for us, especially for the biomedical engineers to work. Okay, and Professor Sriram Venkatesh, our principal, is also well versed in 3D printing and rapid prototyping. I think these two have added some glory to this particular inaugural session. I welcome you, sir, and I think this is my privilege to be a coordinator of this Atal FDP. Thank you, Husna.
Thank you, ma'am. Now I request Professor Sriram Venkatesh, the principal of UCEOU, to address the gathering. Sir.
Yeah, good morning to all of you. Respected our illustrious person, Professor Arun Tiwari Garu. Actually, sometime back, myself and Dr. L. Shivaram Krishna met him regarding the 3D printing only.
Yes, sir.
Well, we are happy to see you, sir, after a long time. And the head of the department, Dr. Suman, and the course coordinator, Professor Malini Madam. Actually, this is the FDP program, first, I think, in the biomedical engineering. And we have finished 2 programs with a similar title, Atal FDP on 3D printing and design by mechanical department, Dr. L. Shivaram Krishna, coordinator, and myself also involved in that 2 programs. This is the 3rd program we are completing from the college. So before, I think this is a subject of interdisciplinary mechanical engineering, biomedical engineering, and even all other departments also. So recently, we have introduced an open elective, that is 3D printing technology. So the 3D printing technology, actually I opted for the students of other than mechanical engineering. So there were actually 60 plus students from civil engineering opted, and biomedical, I think some students, CSC some students, electrical some students, EC some students. But more interestingly, civil engineering students have opted almost 60 students. Total, I think 73 students were there in the open elective. This is very, very emerging and important technology. And we thank the MHRD Government of India. The Osmania University has been sanctioned RUSA, that is the Rashtriya Uchatar Shiksha Abhiyan. So in English now, it is the National Higher Education Mission. Government of India, Ministry of HRD initiative. Under that, no, because of Osmania has got A plus grade by NAC with a CGPA of 3.52. So in the country, only 10 universities have been selected for RUSA under component 4. Component 4 is nothing but quality and excellence in select state universities. So under that, we have been sanctioned 100 crores, and the remaining 7 crores is for faculty development, 100 crores for overall development of the university. So having experience in the 3D printing area since 2008, so myself applied for Center of Excellence in that RUSA. So now, earlier the center was upgraded to now Center for Product Design, Development and Additive Manufacturing, CPDDAM, and by adding 3 more machines with the help of RUSA funding. So almost 6 crores have been sanctioned to the center, and it has been inaugurated by Sri Naveen Mittalji and Honorable Vice Chancellor in the last month. It is housed in the TDC building of this University College of Engineering. So I think biomedical engineering students also are coming forward to take some help in doing their research work, ME project research work. And the center is being established under RUSA funding, but the participating departments are both biomedical engineering department and mechanical engineering department. So biomedical engineering department also, Dr. Suman is also involving, and after Professor Venkateshwar Rao retired, Dr. Suman is also engaged in the activities of CPDDAM. So that is very, very important thing. And most of the cases now, most of the applications, if you look at, the more than 50% applications are from biomedical engineering department. So the doctor from Warangal, the Guardian Hospital, we have built a hip joint. They have estimated that why the bone is decaying. So they did not understand why bone is decaying. And after 3D printing, so original bone and after erosion, they came to the conclusion that this was due to the TB. Similarly, we have developed the skull for the care hospital patients and also pioneer dental hospitals, and most of them are coming forward to see the 3D printing facilities and also building the implants with the plastic. So recently, we have built one scaffolding structure for the Bangalore doctor and dental doctor, and we are also working on some important thing is like artificial heart. So that is going on, and this is the actually research area where we are engaged. But all 4 research scholars with the funding from RUSA, 35,000 rupees per month, they are working in the center, and 2 machine operators also there. So interestingly, we have procured a metal 3D printer. So metal 3D printer is imported from Germany, Lübeck, and it is SLM 280. And this machine we are widely using for not only for BEME projects, defense DRDO also, they have approached us. So we have quoted some price, and they are also into the facilities, we are extending facilities to them for aerospace and defense applications. So these are some of the highlights about the center. But coming to the college, we have 6 programs. The college is established in 1929 after 12 years of establishment of the Osmania University. That is, the Osmania University is established in 1917, and after 12 years, the engineering college is established with the beginning of civil engineering department. Later on, 5 courses, 5 programs have been added. That is mechanical, electrical, ECE, CSE, BME. So recently in 2021, after a gap of almost 30-40 years, we have added BE in ANML, Artificial Intelligence and Machine Learning, and also BE Mining Engineering. So these 2 programs have been added recently with effect from this academic year, 21-22. And also the University College of Engineering has been executed TechCube, Technical Education Quality Improvement Program, around 40.68 crores of projects, phase 1, phase 2, phase 3. We have executed successfully, and 3 crores of rupees worth of R&D projects through UGC, DST, CERN, Spark are ongoing. So this is actually very interesting part of thing, that is our faculty are engaged in R&D activities apart from their teaching. So because of RUSA also, we have been sanctioned around 12 crores to the college for infrastructure and setting up of centers of excellence. One is on 3D printing, other one is cyber security, cyber law, other one is A&ML, and one more mini center in the college. So these are the some of the highlights of um, the profile of this college. And 3D printing anyway. I think all 5 days of the lectures, and if you want to see, okay, if it is a virtual one, we can't. But otherwise, if there is a possibility of looking at the center, so we are ready to show to the take them to the 3D printing center, or otherwise the virtual videos also available. We will play to showcase the facilities available at our center. So we have almost 5 printers are there. One is metal, remaining is two is liquid based, other one is two powder based, one is solid based powders. And so Dr. Suman also knows. Professor Malini also are welcome to see on the lab, and also if any session is free, we would like to give a demo, live demo on various missions. I don't know whether slot is available or not, but anyway, but it's an interdisciplinary research we have to take. And biomedical engineering is from the beginning, no, they are actually forefront in the innovation and incubation. So 5-6 ideas also incubated, and I'm after taking charge as a principal, no, I'm going to encourage all the faculty students who are engaged in innovation and research. Definitely they will be given some incentives or awards. So we thank the AICT for sanctioning such a program to our institution, and also the congratulate Professor Malini for taking initiative to apply this wonderful program, which is useful to the not only students but for the society, particularly in healthcare industries. Thank you very much.
Thank you, sir. We'll definitely thanks for the offer. We'll definitely try to include the virtual session of your lab. Okay, we'll sort out in a day or two, and we'll let you know the exact timing so that we can have that session too. Okay, thank you, sir.
Thank you, sir. Now I request our chief guest, Dr. Arun K. Tiwari, Secretary, Care Foundation and Platinum Jubilee Mentor, to give the keynote address. Sir, please.
Good morning to everyone. It's a great moment for me to meet my friends, Professor Sriram, Professor Malini, Professor Suman. It's a wonderful feeling, and I must express that first. See, these days I am not going anywhere because I have some cardiac problem, and I'm not able to move out of my house. So a few days back, I was particularly low and wondering what can be done. And suddenly I got the mail from Suman, and that is how you are always taken care of. So for me to participate in this event is a wonderful experience, and I'm starting by sharing my happiness and the importance of this kind of an interaction. I'm a mechanical engineer, and I worked in missile program. And my good fortune was that at a very young age, I was spotted by Dr. APJ Abdul Kalam. and he mentored me. Then in 1992, when he became the chief of DRDO and moved to Delhi, he told me that you should come out of the missile program, and gave me a bigger responsibility of interacting with the medical experts and try to do some indigenous products and technologies which are affordable. We selected some 5 areas, and one of that became a success, that is the coronary stent. The Defense Metallurgical Research Laboratory in Hyderabad, Dr. Venugopal Reddy, he made the alloy which essentially must not have any traces of delta ferrite, because blood in the artery is very rich in oxygen, and if there is any trace of delta ferrite is there, corrosion will take place. That was the challenge. So once that metal was made, making a stent was not a big deal. Now it created a sensation because even things like bone plate and screws, they have been imported from foreign countries. So making a stent which goes inside the coronary artery was sensational in 1995. And I received with Dr. Somaraju, the cardiologist, both of us were given the DRDO award for 1997 with the hands of Prime Minister Atal Bihari Vajpayee. And today, when I'm talking in this forum, AICT Atal Faculty Development Program, I have a very good feeling of remembering Prime Minister Atal Bihari Vajpayee also. I could stand in front of him because of the work done of making a coronary stent. So it is eventually your work, what work you do, that decide your place in this world. Not your family, not your children, not the position you occupy. I mean, this world is move very fast. Today somebody is sitting in some position, yesterday somebody sat on the same position, tomorrow somebody else will sit on that position. And as a teacher, all of you must be knowing that every year different students sit in the class. Only you are the constant factor there. So life is changing. So in this changing life, that good work which has been done, it becomes your identity, and people love you, people respect you for that kind of work. So this is the very important thing to understand, that why we remember only Dr. Kalam. There have been so many presidents, there have been so many chiefs of DRDO. We don't remember them, but we remember Dr. Kalam because he left behind the good work for everybody for which he is remembered. So I dedicate this today's lecture to the memory of Dr. Kalam, and request to show the slide number 1. Who is handling slides, please?
Yes, sir. Yes, sir. Mr. Harish is doing that. He'll do that, sir.
Yeah. So, as you can see, the biggest thing which has happened when the new millennium start is the convergence of info, bio, nanotechnologies and cognitive science. This is an event which to me marked the beginning of the third millennium, and information technology, everybody is experiencing it. Your mobile phone is a big computer. You can do, I mean, you are not even using 2% of the capacity of the mobile phone which you are carrying. And this lecture is possible because of this virtual environment, virtual ecosystem, and coupled to that, the nanotechnology, we are able to see almost everything at the nano scale. The coronavirus pandemic, within months, picture of the coronavirus was shown. I mean, everybody knows now. My grandson, who is 9-year-old, he knows what is coronavirus. Because of the nanotechnology, because of the convergence of the technology, that there is a spike, and that spike is called corona, and there are 3 folds in that: S1 protein, S2 protein. All these things are possible to know that because of the convergence of the technology. I have also attended the one very nice workshop organized by the Department of Biomedical Engineering, Osmania University, about the neural signal processing. So somehow this department is blessed with some of the very nice teachers and some of the very open-minded students. This combination, some blessings are there, and as the convergence of the technology is progressing, this department always, I find, that it is handling with those frontier areas of whatever is happening around them. So coming back to the topic of today, in 2014, we were fortunate to have Dr. Kalam come to the Biomedical Engineering Department. Kindly show the slide number 2. And he is with the interacted with all the students. It was a festival like a day, and on that day, Dr. Krishna Ella was present, who is the chairman and managing director of Bharat Biotech. Today, you all know him because of the corona co-vaccine, which has been developed by his company. And we also had that day Dr. Varshney, Rajiv Varshney from ICRISAT, who is considered as one of the top scientists in the world as far as the genetics of the seeds are concerned, seeds and plants. So both these people and Dr. Kalam were there in the department on the 1st August 2014. And this picture is taken on that day, and I fondly remember that occasion. And it really, I mean, it gave a goosebump feeling that we have been a part of this beautiful journey. Coming to the topic of the day, as you very rightly pointed out, that it is called additive technology, additive manufacturing. On the layer by layer, you keep on depositing the different atoms. And I have been to the facility in Osmania University, as Professor Sriram mentioned, and that time it was not for the metals. Now it is for metals also. And now the trend is that we have to take it to the cellular level, where we can handle the live cells, and we deposit it on different kind of scaffoldings, and so that we can make tissues, and we can make the replacement of damaged areas. The big possibilities is there. So next is going to be the BioLink, and I request for the 3rd slide. You see, there are multiple areas, and medical application of 3D printing, possibilities are immense. You can prototype, which you are already doing. You can manufacture the implants. You can use it for the pharmaceutical development. Exactly one tissue you can generate, and subjected for the particular interactions of the pharmaceutical agent which you want to study. I have one friend, I will be introducing him to you. He is working on these kind of tissues, and you have the National Institute of Pharmaceutical Research, NIPER, in Hyderabad. I have spoken to the director of NIPER, Dr. Sashibala Singh, and very soon I will be connecting both of them with you, and we will be launching something interesting in that area. In 1970, if I look back, the National Aeronautics and Space Administration in the United States, popularly known as NASA, they have articulated on the different technology readiness levels. See, technology is not some end product. Technology is a process, like a tree. Ariji, you can show the next slide. And there are 7 stages, and starting from basic principles, understanding of basic principles, which we have already into that basic principle stage at this point of time as far as the 3D printing is concerned, or additive manufacturing, whatever you want to call it. And then the technology concept and application is formulated, where I am going to use it. I think we have crossed that TRL 2 also. Technology readiness level 2 also we have already achieved. The third thing is laboratory testing of prototype components or processes. That has already started. Some work has already been done. And now in the next 2 to 3 years, the center at the Osmania University is going to get into some very specific and real life collaborations, and we will be the first in the country, as we are celebrating. I mean, we are remembering with reverence that the first coronary stent was made by Dr. Kalam and Dr. Somaraju. Similarly, some names will always be engraved in history, that first time this particular prototype, this particular implant, this particular tool, this particular tissue, this particular pharmaceutical validation and experimental technique has been developed at the Osmania University in year 2022, 23, 24, 25. I mean, this is the time when this kind of milestones we have to be, we will be creating. Then comes the laboratory testing of integrated system. In that stage, these products and implants become the part and parcel of the patients, and they become the clinical practice. I think this is the sum and substance and the goal as far as the department and the center is concerned. And beyond that, industry steps in. And beyond that, department cannot really go forward, and industry has to come. Industry has to come, investment has to come, and later in the towards the later stage of the lecture, I am going to touch upon that point. So coming to the next point, next slide you can put. As Malini ji has observed, additive manufacturing was first developed in 1980s, and it involves taking a digital model or blueprint of the subject that is then printed in successive layers of an appropriate material to create a new version of this object. It was initially used to develop computer hardware and later become the axis of prototype development in the industry. There is no industry in which 3D printing is not used today. So I have particularly selected this diagram to give you an idea that first you have to reach this stage where exactly what you want to achieve. As far as the body parts, tissues, bones, joints, filaments, ligaments, all these things, there are so many things in body. Don't jump onto organ. First, let us talk about tissues. First, let us talk about small bones. So all these things, first you have to make a model. And that is the first stage, which almost we have reached that stage. Only thing is now we have to quantify. This is pancreas, this is kidney, this is the lung. So this is how we have to get into the elementary level prototyping. 3D printing has many functions in a variety of industries, and there are three main applications I can see in the medical field. One is to improve the lives of those reliant on the prosthetic limbs, then to produce specialized surgical tools, and to provide neuroanatomical models for complex surgeries. As on today, with the metal 3D printing already available in the center, all we need to do is get into some 2-3 techno-commercial agreements and make sure that in all these three categories, the prosthetic limb, surgical tool, and the neuroanatomical model, we deliver few products, publicize them, make money out of them, and let the people feel that if they need anything, this is the place where we have to approach, and these are the people who are going to deliver it to us. And I am going to add into that tissue model for pharmaceutical research, which he has already mentioned that I am going to link all the people, and the drug delivery systems. Because most of these cancer drugs, they are highly toxic. Even the best of the drugs, which comes for 10 to 15 lakhs rupees per person per round of therapy, and a body has to suffer. So 3D printing, excellent opportunities it presents, by which overcoming, circumventing, bypassing the damage to the other cells and tissues, the medicine can be exactly given to the place where the cancerous cells exist. So these are the two areas where we have to be focusing in the next 1 or 2 years' time. So far, scientists have printed mini organoids and microfluids model of tissues, and also known as the organs on chips. Some of these models are used by pharmaceutical companies to test drug before moving on to animal studies and eventually the clinical trial. And let's fix a deadline of 6 months, next 6 months, when the first organ on chip comes out of this center in a collaborative project with the ESIC Medical College, which is a most emphasized program by the Prime Minister after the pandemic. There are hundreds of medical colleges coming out in the government sector in the country right now, and it is important to link with these setup, because most of them are professors taken from the institutes like All India Institute of Medical Sciences and other premier institutions, and they have very rich experience. Their commitment is unquestionable, and whatever you succeed in there, it is going to be multiplied with very big numbers. My generation has seen the privatization of healthcare. We have seen how Apollo Hospital was made, how Care Hospital was made, how Yashoda Hospital was made. And the coming generation, the students who are students at this point of time, they will be seeing one government hospital and 500 bedded, one government medical college and 500 bedded hospital in every district in 2 to 3 years time from now. So time is changing. So we also have to orient ourselves in such a way that instead of talking to randomly some doctor, some head of the department, some private hospital somewhere. Let's go in a focused way. Let's put down our things together, go to the appropriate forums, get it funded by the government. The department should become a constant funder. So that 10 years, 8 years, 10 years, 12 years from now, you are going to have that kind of tree, and the people who are at that point of time, they will enjoy the fruit. So the future belongs to platform ecosystem thinking. The pandemic lockdown has shown that people are working from home for last more than 2 years, and it did not bring down the revenues or the outcomes of a very large part of the industry. So don't consider yourself that I am a faculty and I am teaching in a particular field and that is the class. I mean, that should be not more than 50% of your career. The remaining 50% is that you should use yourself and your students and your knowledge and your innovative potential to work as a part and parcel of a boundaryless system, which will be, because no single organization is going to do this work. It is too complex, it is too big, it cannot be done by the employee of one organization. So wherever the experts are, they have to be linked, they have to be given task, they have to deliver the task, and they have to receive the money. After the collapse of USSR, the Soviet Russia system, many scientists in Ukraine, many scientists in Belarus, many scientists in Hungary, Czechoslovakia, Yugoslavia, they become freelancers, and for $10,000, $15,000, $25,000, they will do the design of the subsystem, solve the problem which we used to give them, and in 8 weeks time, 10 weeks time, they will deliver the product and receive their money through bank. So this is what is going to happen in this area also, and we have to, it is the time to make it official. It is time to sort it out in all the bureaucratic forums, and there is nothing wrong in that, there is nothing illegal in that. Don't create a situation that we have to do what is required and we are not able to do because some stupid rule is there, some clause is there, somebody is there who is saying how can you do it. The world is all about what can I do it in my life, and nobody should be able to stop me in what I want to do in my life. And it is in the interest of the organization, whether it is a university or it is a government department or it is whosoever, that they allow their human resources to flourish and to do whatever they can do and make money out of it and take the technology forward, take the state of art forward, become the forward agent of the progress. That is the whole spirit of the new India. In the background you can see one book which I wrote last year. It is called India Wakes. Now India has woken up. A engineering student is not confined just to wait for some PWD department or some irrigation department or some electricity board to give him a job. That's how we did in back in 1980s and 90s. Now even before the graduation is complete, you have placement teams in your campus, there is a wide variety. There are there is such a cross fertilization is taking place that it is you to choose what you want to, which area you want to flourish yourself into. So this is the as far as this area is concerned, that is the main message. Show the next slide, please. So as I said that we started from now the center is having the metal bioprinting also. Bioprint, it has done a wonderful work to now go into the stem cell taking into and deposited into a tissue structure. Now this is the work which we have to work, this is the area in which we have to work, and I don't see anything else. This is ready. You are already having all the infrastructure around you. You have to add into this depositing of the stem cell ink part. The remaining things are already available. So let's make a project, let's submit it to Biorec, and what should be that tissue which should be selected. Let's discuss with the faculty at the ESIC Medical College Sanat Nagar. I'll organize the meeting and submit the project. And once the project is available, funding is available, this is one of the best university and one of the best department in the country, who, if you want to be delivered in 6 months, it will be delivered in 20 weeks. That is the kind of track record which this university and this team is having. I have been a witness of electronic and communication department. Wherever we wanted them to develop anything in 1980s, before time it was delivered. And it was a way of thank that a beautiful auditorium was gifted to the department for doing excellent work before time. So this is the area which we are going to get into. There is a lot of work going on into vegetable marine biopolymers. We have a National Institute of Oceanography in Goa. It is a CSIR laboratory. I'll connect them to you, and they will provide you this material from the marine source, which can be used as a scaffolding material. And cellular material you can get in Hyderabad, whatever you want, medical college will give you. And then you have to show that this is what we have made. It is living, it is functional, it is working for 1 week, 1 month, 1 year. And once you publish that, once you demonstrate that, it is not in lakhs and 10 lakhs, 20 lakhs and all. It is going to be in 10 million, 20 million. It is not going to be in rupees, it is going into the dollars. And this is mark my word. This is what is going to happen through you, by you, and you are going to accomplish it. Please show the next slide. Now, we should focus on the exact, see, it is the one is the bone. Bone is the first thing which is going to come. Second are the tissues, collagens and other connective tissues. And in every disease, it is not that the whole thing has gone wrong. Always it is a minor part, a minor portion, beginning of a problem. And with the modern diagnostic techniques, we can catch all these things very early. So it is going to be mostly not the replacement, but repair. And that should be the focus which we should be working on to that. And in conclusion, please show the last slide. It is a, it is a big area. For example, I have taken, because I spent a lot of time with the cardiologist, it is not the question of making an artificial heart. In that process, you are making the physiology of the heart, where the heart is located, where is the diaphragm, what are the, I mean, every heart, everything is how it interferes with the, how it adjusts itself with the lungs, and what is the exact position. And after that, the stem cells have to be re-engineering and reprogrammed, and which are the cardiac cells and which are the other cardiac cells. All these cells have to be deposited, separated, and then we have to make the block of the different cells and use them into that integrated way in the 3D printing. And all these things, when they are assembled together, whether they will become an artificial organ or they will repair the organ or what they will do and all that, let that problem and challenge come from the medical side. It is not our problem. आपका पंचर कैसे हुआ, आपने को कोई टेंशन नहीं है, हम पंचर बना के दे देंगे आपको. That should be the spirit. And with that spirit, let's start working. It's a wonderful feeling. All of our lives are to capture the romance of the day, the fashion of the day, what is happening. In 1980s, electronics was happening. In 90s and 2000, computers were happening. And now 3D printing is happening. And those who will miss it, it is like not smelling a flower in the season of the spring or not getting drenched in the feeling of the rain. It will be so unfortunate. So I am very happy that this initiative has been taken. People from multiple engineering colleges are attending this forum, and let us share this dream that from today onwards, a new ecosystem, we are going to work it out. And I am volunteering to connect you with the best of the institutions in the country and in the world. And with these words, I thank you very much, all of you. And it is such a, you make my spirit really, I was a little depressed and what to do and all that. But now after interacting with you, I realized, oh, there is so much is to be done. So with this feeling, I concluded. Thank you very much. God bless all of you. Thank you.
Thank you, sir, for motivating us and giving us a brief insight on the benefits and applications of 3D printing. Now I request Professor Malini ma'am to please give the vote of thanks. Ma'am, your mic is on mute.
Yeah, thank you, Husna. It is my privilege as the coordinator of the FDP to propose a vote of thanks. On behalf of the department and on my own behalf, I extend a very heartfelt thank you, a big thank you to our chief guest, Dr. Arun K. Tiwari sir, for accepting to be the chief guest and delivering such an inspiring and motivating talk. Sir, thank you for having confidence in us. You have always been a mentor for us and you are like a godfather to our department. Yeah, I must mention our deep sense of gratitude to our principal, Professor Sriram Venkatesh sir, for his valuable address and also extending support to us. And I profoundly thank Dr. Suman, Head BME Department, for extending full cooperation to conduct this workshop. My sincere thanks to AICTE experts for granting us this FDP and also sponsoring the same. I would like to take this opportunity to place on record heartfelt thanks to all the expert speakers for accepting our invitation to deliver the lectures. We are indeed eagerly waiting to listening to them all. I extend my thanks to each and every participant of this FDP, and I hope these 5 days will be fruitful and they will definitely gain a direction to their research in this area. And I also thank all my faculty members and the teaching and the non-teaching staff for supporting me in conducting this workshop. Thank you one and all.
Thank you.
Thank you very much, sir.
Thank you, ma'am.
Yeah.
With this, we come to an end to the inaugural function of the ATIL 3D Printing Academy event.
Yeah, we'll meet at 11:45 for the sessions. Okay, and I also there is a announcement for the participants. The attendance and your performance in the test, which will be conducted on the last day, is essential. So you should have a minimum of 80% attendance and 60% you have to score in the test we are going to give you on the last day. Only then a certificate will be generated on your name. So it is a this is mandatory as a AICTE regulation, and we have to strictly follow them. Okay. Yeah, we'll meet at 11:45 for the lecture. Sir, thank you so much, sir. Thank you so much.
Thank you.
Yeah. Thank you very much, sir. We'll be in touch, sir. Definitely.
Yeah, thank you. Thank you very
Yes.
much.
Thank you.
Yeah.
క్లీన్ చేసిన నెంబర్లు అయితే ఉన్నాయి.
Hello.
Yes, Sailalta, you can start.
Uh, Good morning, everyone. This is Sailalita, Research Scholar of Biomedical Engineering Department. Um, Today I'm here to introduce Mr. M. Venkateshwar Rao, sir. I feel really privileged to introduce sir. Sir is a retired faculty from Biomedical Engineering Department, UCOU. He was retired in 2019. Sir firstly joined in the BME department in 1982 as a JRF, and he has and he was elevated to the position of the head of the department. During his tenure in the department, he has associated with many research projects, including UP projects. He has applied for many patents, and some of them are in the inspection stage right now. And Sir has also published nearly 60 research papers in journals like Springer and Nature View. Now he is actively associated with big grant projects as a mentor, and he is also working on drones and robotic devices for renewable energy plants. So thank you for coming here, sir.
Thank you for the nice introduction,
Thank you.
Salita.
Over to sir. Yeah.
Good morning to everyone. And I am Venkateshwara, and I am a retired faculty from Department of Biomedical Engineering. And now my topic is on manufacturing techniques for 3D printing. And here, the manufacturing of any product, if you see, it can be split into several parts, and the parts can be manufactured by two major processes. One is called as additive processing, the other one is what is called as subtractive processing. And very recently, the additive processing is coming into picture, but earlier days only subtractive manufacturing we were using. And in the particular context, if we see the subtractive manufacturing, we'll take a log of material. That material could be either wood or metal or otherwise any other material, and that material will be tilted to your final desired shape by using what is called as milling, turning, drilling, or otherwise computer numerically controlled machines. Okay, so by using these techniques, we are removing the metal or otherwise the material from the block to get the desired shape. Okay, so and in this particular process, what is going to happen is we are wasting a lot of material by the removal, and all that removed material will become what is called as a waste material, and that need to be scrapped. And now when it is coming for the additive manufacturing, it is what is called as 3D printing nowadays. It's a form of additive manufacturing. In this particular process what we'll be doing is we'll make the material to join process the joining of material, joining the materials to make an object from 3D model data, and this process is done by layer. Here, if we see this particular picture, the first layer is built first, and on top of it, second layer, third layer, fourth layer, fifth layer, and the new layer will be on top of it. And in order to print this particular design, we are having here a printer, and that printer will control the print mechanism and give the shape of this particular top layer. Okay, and this is what is called as additive manufacturing, and this is the just a gist of it. And now let us see what is actually defined by the technical teams. Okay, additive manufacturing by American Society for Testing and Materials. It has defined it as a process of joining materials. Materials could be anything, and to make objects from 3D model data, usually layer upon layer. Already I showed the first picture, as opposed to subtractive manufacturing methodologies such as traditional machining. Okay, and the same thing can also be sometimes called as rapid prototyping. This term was used in the beginning of the professional use of the technology because the main application was the manufacturing of prototypes. Okay, earlier this was used only for prototyping of some parts and mock-ups and sample parts. Today, most common terminologies are either we can call it as additive manufacturing or as rapid prototyping. Okay, and I guess both the definitions are valid as the team goes first. So here, if we see the types of additive manufacturing, the additive manufacturing process itself is divided into three categories based on the material, and we can use liquid basis, or otherwise powder-based raw material can be used, or otherwise solid-based raw material can be used. So that means we are having liquid-based raw material, or otherwise powder-based raw material, or otherwise solid-based raw material. If we are using liquid-based materials, then what are the techniques that we are having means stereolithography and jetting systems, direct light processing methods. And if we are going for powder-based things, we are having what are called as selective laser sintering, three-dimensional printing, fused metal deposit systems, electron beam melting, selective laser melting, selective masking sintering, selective inhibition sintering, electrophotographic layered manufacturing, high-speed sintering. And still there are so many other methods, but these are the main methods what we will be using. And the solid-based, if you see, for the solid-based materials, we are using fused deposition modeling and sheet stacking technologies. Okay, and if we go for stereolithography, it is widely recognized as the first 3D printing process. Okay, and it was certainly the first to be commercialized. And I mean, when it comes to commercial production or otherwise the market capabilities, it's the first 3D model that has been commercialized into the market. Okay, stereolithography is a laser-based process that works with the photopolymer resins. So we are having photopolymer resins, and that photopolymer resins, when they are exposed to laser or otherwise in certain cases natural light, there will be what is called as a polymerization. And because of that polymerization, the liquids will get, resins will get solidified, and that forms as a concrete structure. And that react with the laser and cure to form a solid in a very precise way to produce very accurate parts. Okay, and it's a complex process, but simply put, the polymer resin is held in a vat. It's a container with a mobile platform inside it. So a mobile platform will be there in the vat, and then on the mobile platform, a laser beam is moving in an X and Y axis across the surface of the resin according to the 3D data supplied to the machine by what is called as an STL file, whereby the resin hardens precisely where the laser hits the surface. So wherever the laser hits the surface of the resin, and that particular part will get solidified. And once the solidification is over, the platform will be lowered a bit. Okay, and that what is meant by that bit means it is defined by your z-axis resolution. Once the layer is completed, the platform within the vat drops down by a fraction. Okay, that fraction could be either 0.1 mm or otherwise 1 mm, and it is defined by your system resolution. And the subsequent layers is traced out by the laser. This continues until the entire object is completed, and platform can be raised out of the vat for removal once the printing process is finished. And because of the nature of the SL process, that is stereolithographic process, it requires support structures. Say whenever you are having a beam or otherwise a overhanging structure, it requires a support because the material can't stand there, and it may slag or otherwise it may have a drooped nature. Okay, in order to avoid that particular thing, we need to have what are called as support structures, and those support structures we have to use in the design form itself, specifically those with overhangs and undercuts. Okay, these structures need to be manually removed. I mean, once the product is over, finished, after removal from the vat, we need to remove these support structures by manual removal. Okay. In terms of other post-processing steps, many objects of 3D printed using SL need to be cleaned and cured. Most of the 3D printed products need to be cleaned and cured in order to get that surface finish, or otherwise in order to get some flaws removed. Okay, we have to clean the built up product, or otherwise it need to be cured in order to remove certain defects in it. Curing involves subjecting the part to intense light in an oven-like machine to fully harden the resin. Because here, as we might be using either laser or otherwise the natural light, curing process may not be completed because only for short duration it is exposed to UV rays, or lasers or otherwise natural light. So in order to make that solidification complete, after removal of the product from the vat, we need to expose it to the intense light in order to solidify it completely and in order to harden that particular product. Stereolithography is generally accepted as being one of the most accurate 3D printing process with excellent surface finish. It provides excellent surface finish, and at the same time it also provides what is called as accurate dimensions. Okay, however, the post-processing steps required and the stability of the materials over time, which can become more brittle. As we are using the light-dependent photopolymers, the materials may become brittle after a certain amount of time. Okay, that means that they can't be used in months. They'll have after that life expectancy, they may become brittle and then they lose that particular structure. Okay, stability of the metals is also they degrade with time. And this is the instrument how it looks like in principle. Okay, so here you are having what is called as liquid resin, and in the liquid resin you are having a platform. That platform will be moving up and down. Initially, here this will be in the top position, and very thin layer of this liquid resin will be on the platform, and the laser scanner system is there, and that laser scanner system will project a laser beam onto the top layer, because the platform is in the raised condition, and only a very thin layer resin layer is there on the platform. So as and when the laser beam touches the superficial layer, and that layer gets solidifies, and then what will happen is it will be, once the entire platform is scanned, then the bed will be moving a bit lower, and then new liquid resin will be there, and again the laser beam will be scanning the entire surface by the control of your computer. Okay, this process is continued and until the product is finished. Once the product is finished, what we will be doing is we will be raising the bed again onto the top, and then we will remove the product from the bed. And after that, we will be cleaning the process and then cleaning the product. And if any defects or otherwise any surface is not good, then we will be using some manual methods in order to remove those defects. Okay, so this is how the stereolithographic technique works. And then if we see the second thing, what is called as digital light processing, it is similar to your stereolithography, in that it is a 3D printing process that works with photopolymers. Okay, and the major difference is the light source. With the stereolithography and then DLP, the major difference is nothing but your light source. In that you are using your lasers, and whereas here you are using a normal light source. Okay, this digital light processing uses a more conventional light source such as an arc lamp. Okay, arc lamp is nothing but a normal lamp which produces very high intensity of light, and with a liquid crystal display panel, okay, or a deformable mirror device which will project the layer by layer drawing onto your surface. So whenever the surface gets that particular drawing onto that particular thing by means of light, and there that structure gets solidified, and that structure will be, once it gets solidified, it will be going down, and then again the new liquid will be coming into picture, and again you will be having the same second layer will be focused onto there, and then on repeated focusing, what will happen is as the structure goes on getting building up, okay, which is applied to the entire surface of the vat of a photopolymer resin in a single pass. That means instead of scanning in X and Y directions as it is happening in the stereolithography technique, here the entire one layer will be focused onto the surface at a time. So because the time saving will be very high, and that's why this is very fast technique. Like SL and DLP also, in SL it is producing highly accurate parts. Here also it produces accurate parts with excellent resolution. Okay, its similarities also include the same requirements for support structures and post filling. As it is happening in stereolithography technique, here also it requires overhangings and otherwise any structures which need support structures need to be there, and post curing also it's same as that of your stereolithography. However, one advantage of DLP over SL is that only a shallow vat of resin is required, okay, to facilitate the process, which generally results in less waste and lower running cost. So here, if you observe, here I showed the thing also. And in DLP, what's happening is here the photopolymer container is very small, and at the same time the stage is on top, and the stage will be in contact with this particular thing, and then this light source is focusing onto the DLP, and here the first layer will be there, and that first layer will be focused onto this particular thing, and then it will be attached onto this stage. And the first layer is over, the stage will be moving slightly up, and again the second layer will be, and like that the layer by layer the material will get attached to one layer after the other onto the top, and then once ultimately the product is finished, then the stage will be moving up, and then the product will be removed from this particular stage. So here if you see the photopolymer container, it is having very small quantity of material. And whereas if we see the stereolithography technique, here the entire container is having liquid resin, and once the liquid resin is exposed to laser beam, though it is focused, it will have some sort of unwanted reflections, and those reflections will make the other material, liquid resin material, also slightly not usable for the again and again. So this entire material will get wasted in the case of stereolithography. Whereas in the DLP2, that's not happening, and only small quantity of photopolymer is sufficient to prepare the product. Okay, and laser sintering and laser melting. This is another technique. Okay, and there are two methods what I am discussing here. Both are interchangeable terms that refer to a laser-based 3D printing process that works with powdered materials. And this is mainly meant for powdered materials, not for liquids anymore. And the laser is traced across a powder bed of tightly compacted powdered material according to the 3D data fed to the machine in the X and Y axis. Same, here instead of a liquid, here it is a powder bed, and that too tightly packed. And the top laser in both X and Y directions. As the laser interacts with the surface of the powdered material, it sinters. Sinters means it slightly melts and then it gets fuses with the adjacent particle. So as it gets fuses, so they are attached one to the other, and all the particles as they are attached, that forms as some sort of a sheet. Okay, and that sheet is nothing but as per your drawing in that particular slice. Okay, that is done by your 3D data supplied to the machine by means of X and Y axis movement. And the particles to attach each other forming a solid. As each layer is completed, the powder bed drops incrementally and a roller smoothens the powder over the surface of the bed prior to the next pass. So once the one layer is finished, what will happen is the dropped by certain extent, and then next powder will be smoothened onto this particular roller bed, and a roller will be there, and that smoothens that spreads the powder onto the surface, and again the X and Y next layer will be forming, and again it gets fused to the bottom layer as well as adjacent particles also gets fused. Okay, so this how the thing will be going ahead. Okay. The build chamber is completely sealed as it is necessary to maintain precise temperature during the process specific to the melting point of the powdered material of choice. And here, the material, whatever the material you are using, it could be a metal or otherwise polymeric powder. Okay, whatever the material you are using, it has to get fused to the adjacent particle as well as to the bottom surface. So in order to get that fusion temperature, the temperature need to be elevated based on the material what we have chosen, and that temperature should not go waste. For that reason, the chamber is completely sealed by external disturbances, so that precise temperature can be maintained for the process to be finished. Okay, and once finished, the entire powder bed is removed from the machine, and the excess powder can be removed to leave the printed parts. So once the process is finished, the product is raised onto the top, and then the object is removed from the bed. And here, what is happening here? The whatever the cavities we have not melted, those cavities also will be having powder. That powder can be removed by brushing or by using certain other removal materials. And once all of them they are removed, then your product is visible and it is useful. The key advantage of this process is that powder bed serves as an in-process support structure for overhangs and undercuts. And whereas in the earlier two methods, you require what are called as support materials in order to have overhangs and then some undercuts if they are there. But in this particular case, the powder itself forms as the support structure, and there is no need for any support structure as it is need to be built. And the powder itself forms as the support structure, and therefore it is not required to remove that support structures by means of cutting or otherwise by using abrasive methods. Okay, and therefore complex shapes that could not be manufactured in any other way are possible with this spectral process. So because any overhanging or otherwise any small void is required, all that can be done by the spectral thing very easily. So for that reason, this spectral method is useful for very complex shapes, and at the same time, with internal voids or otherwise air gaps, or otherwise if you want to have overhangs or otherwise a structure dropping from the top, all that can be built very easily by this particular method. There is no need of any support structures in this particular case. Okay. Because of the high temperatures required for laser sintering, cooling times are considerable. Because as we are going to melt the material, and that material could be either polymer or otherwise metal, the temperature is elevated to very high temperatures. As the temperature is very high, the material need to get cooled. Okay, so for that you have to spend some time. Okay, that means the product has to get cooled. So for that, considerable time is required. Furthermore, porosity has been an historical issue with this process. Porosity means there could be some small gaps between the particles. Though they are fused, there could be some small gaps because the fusion is not completed, and then we are not applying any force. So as we are not applying any force, there could be some voids, and those voids makes the porosity of the ultimate product. And while there have been significant improvement towards fully dense parts, there are certain methods we can follow in order to remove those voids. But even then, those voids will be, they are inevitable. They are there. Some applications still necessitate infiltration with another material to improve mechanical characteristics. To remove these voids or otherwise to get a better product, we have to have some infiltration materials. By using those infiltration materials, we can remove into the mechanical characteristics of this particular product. Laser sintering can process plastic and metal materials. Already we have discussed. Although metal sintering does require a much higher powered laser and higher in-process temperatures, because metal melts at very high temperatures. So whenever you are going for metal related products, we have to have what are called as metal sintering, and metal sintering requires very high temperatures, and then whereas with plastics, that high temperatures are not required. Parts produced with this particular process are much stronger than stereolithographic or digital DLP techniques. Although generally the surface finish and accuracy is not as good. In the case of stereolithography and DLP techniques, you are having surface finish very good finish, but at the same time they are not mechanically that strengthy. Whereas with this particular SL or SLM3 techniques, the product is stronger than the thing, but at the same time surface finish is not that good. And here you are having the powder is here. You can see the powder here in this particular container, and here the product is built on the other platform. Okay, here the platform is having the building area, and these two are separated by means of support structures. And here this will be in the first at the top, and here the powder will be rolled out onto this particular platform, and the laser beam will be focused onto this particular thing. And first this layer will be built as the platform is at the top. And once this particular this thing is finished, then what will happen? It will be slightly lowered, and again this will be slightly elevated, so that the next powder layer will be moved on by this roller onto this particular thing, onto the building platform area. And on top of the first layer, the second powder layer will be there, and that is not fused because it's just drawn from this raw powder bin to the build-up platform. And now again the second layer scanning will be done, and the second layer will be built out. And once the second layer is over, again it will be lowered, and again this piston will be moving up, and the roller will go again the top layer onto this particular thing, so that the third layer, fourth layer, like that, the entire process will be built up. And once the entire process is built up, here you can see this entire material, dull finished material, if you see, that is not fused. Okay, and only the laser beam will be focused onto this particular surface, so that only that particular material will get fused to one to other in the adjacent area, as well as to the beneath the surface also, so that it gets attached to the bottom surface, as well as adjacent molecules also attached as per your requirement. That requirement is again sent by your computer system. Okay, the computer system, whatever the product design you have fed into the computer system, that will decide, and that will provide the laser beam, and that laser beam will decide your final product. Okay, and here this the material whatever you have left over here, that will help to see that no support structures are required, because this material itself will add as a support structure, and this can be removed very easily. But at the same time, here the surface finish is not that good, as already I have explained. This is a laminated object manufacturing. This is also a rapid prototyping system developed by Helsys Inc. This is a company, and this company has developed this particular product. In it, layers of adhesive coated paper. That means here you are having 3M tapes and all the other tapes they are available, glue tape they are available. Similar to that, here we are having adhesive coated paper or plastic or otherwise metal adhesive sheets are there. And those are laminated one onto the other, are successfully glued together and cut to shape with a knife or a laser cutter. Knife means don't think it's ordinary kitchen knife. It's a sharp-edged object which will be used normally in industry. And that knife or otherwise laser cutter is used in order to get the top structure. Once the top structure is over, and again what is that we'll be doing is we'll again take one more adhesive coated paper or plastic or metal, whatever we are using. Again, one more layer you will be fixing up, and that will be again cut into the shape. And again one more layer, like that we will be building up the product. Objects printed with this technique may be additionally modified by machining or drilling after printing. Because here sometimes what we will be having is we may not have the internal cavities, or otherwise sometimes the required structure we will not be getting. So in order to get the required structure, what we'll be doing is once the product is finished in a rough manner, that particular product is machined by using the regular mechanical process such as drilling, milling, or otherwise surface finish, etc., etc. Okay, typical layer resolution for this process is defined by the material feedstock and usually ranges in thickness from 1 to a few sheets of copy paper. That means a normal paper thickness if you see, and that sheet thickness is nothing but your resolution in the vertical direction. And in the X and Y direction, that is defined by your knife and then or otherwise laser cutter, that will define that particular thing. Okay, so here the papers are attached one to the other, and once the paper is attached, immediately you will cut and then remove the unwanted areas, and then like that the structure is built. And once the structure is over, then what that you will be doing is once a rough structure is finished, then machining, drilling, and etc. is done in order to get the final product. Okay, this is how this is. So here, this is the glued paper. This is input rail, and this is the output rail. And here, what is that? These are take-up rollers, what we'll call it as. And this roller, what you will be doing is you will be bringing up the new material here. And on this particular thing, you will be attaching this particular thing to this particular thing, and then it is cut as per the required shape. Okay, once this particular thing is over, the remaining paper will be there. That paper will go into the take-up wheel. Okay, so the again second new part of material will be coming over here, and that will be glued first, and then afterwards the cutting is done by here laser cutting I have shown here. But whereas here sometimes other methods of cutting can also be adopted here. Okay. Now let us go to the next technique. That is what is called as binder jetting. And there are two 3D printing processes that utilize jetting technique. Jetting means here a jet of liquid can be taking place, and that jetting of the liquid will be forced onto the material where you have to glue some matter. Okay, binder jetting, where the material being jetted is a binder. Binder means which will add one to the other, and is selectively sprayed into a powdered bed of the part of material to fuse it a layer at a time to create a print the required part. So this binder material, what we'll be doing is we'll be spraying at required places, and then that fuses the adjacent particles, and then as it is selectively sprayed, the layer is selectively we got the layer as per our requirement. And once that is over, the next layer will be fused, and like that the entire particular process is finished. As is the case with other powder bed systems, once a layer is completed, the powder bed drops incrementally, and a roller blade smoothens the powder onto the, similar to your the other technique what I showed earlier. This in this also what is happening is here your powder is a new set layer of powder is rolled onto this building platform, But whereas here in this particular process, in this particular process, what's happening is it drops incrementally, and then a new powder will be spread onto the old one. And again, the instead of laser there, which will fuse the material, here we are using a binder material. That binder material will be sprayed as per our requirement, so that the adjacent particles are fused instead of melting and then getting fused. Here we are using the binder material. That's all. Okay, and this particular process will be done with each layer, and that entire thing is formed. Advantages to this process, like the SLS, include the fact that the need for supports is negated because the powder bed itself provides the functionality similar to that of your earlier technique. Okay, a range of different metals can be used, including ceramics. Nowadays, if you are going to exhibitions or food stalls, their chocolates are printed as per your required structure. Okay, that printing is done in this particular process. A further distinctive advantage of the process is the ability to easily add a full color palette, which can be added to the binder. So to the binder, what you can do is you can add different colors as per your requirement. So different colored layers you can have as per your requirement. The parts resulting directly from this machine, however, are not as strong. They are not strong because it's only binding material which will hold that particular thing. And that binding material, if it is not properly cured, okay, for various reasons, even each binding material will have its own shelf life. If shelf life is lost, is exceeded, then the binding property is not that good. So this is not strong enough. This is not strong enough, and the sintering process, post processing to ensure durability. If you want the durable product, then sintering process is also required, and post processing is also required in order to make that better thing. Okay, the same technique, but here what that you are doing is here you are having the material here, and here the spread of the material is done, and after that here if you see inkjet printhead is there. This is a binding feeders that different colors I have showed here, and from these binders, from the selective colored material will be dropped onto this particular thing, and so that the material will get fused. But at the same time, the sideway material is also there. That sideway material is just giving a support structure used again and again, but little processing is required if you want to use the material used once as the fresh material. Okay, so here this powder supply is there in one bin, and then the actual build question is here, and then here through this inkjet or printhead we are providing that binding material over the material. Okay. So this is the other method, fused deposition molding. This is called as FDM, and free form fabrication, what is called FFF. 3D printing utilizing this extrusion of thermoplastic material. Okay, this is a thermoplastic material. It easily melts, and then it can be melted, and then it can be again reformed as a solid form. Okay, and this is the most popular name for the process is fused deposition. The process works by melting a plastic filament, and this is available in the form of filament that is deposited via a heated extruder. Okay, normally in almost all plastic industries we will be using the extruder mechanisms. In the extruder mechanism, what we will be having is we will be having small plastic pellets, and then those plastic pellets are melted, and then it will be forced into a mold, and that mold will have cavities, and in those cavities the molded plastic will get fixed, and then after that the from the mold your product is removed. But here what that you are doing is the plastic filament is like a wire. It will be continuously passed on to the heater, and that heater will extrude the material, and that material will be building up the product as per your requirement. And this heated extruder will be moving in an X and Y directions, layer by layer. So once one layer is finished, and the second layer will be coming, and from the first layer to the second layer, the bonding will be happening because the material is in the molten form. Plastic material is in the molten form. Okay, and the layer X and Y direction is movement data is supplied by your computer through your commands. Commands means you will not be using. This is automatically done by the software itself. Okay, data supplied to the printer. Each layer hardens as it is deposited and bonds onto the previous layer. So onto the previous layer, the new layer will be bonded. And again, once this layer is over, next layer is formed like that. Okay, and here these techniques process require support structures, because this requires support structure because it's a molten material that is attached on top of the previously deposited material. So if you are having more hangings or others, any other thing, there is no support beneath that. So as there is no support, we have to provide the support structures, and those support structures need to be. We can use some other material to provide the support structures, or otherwise the same material can be used. And if you are using the same material, you need to remove that particular material by cutting, or otherwise by using certain other mechanical regular processes. Okay, if you are using water soluble material as a support structure, it can be kept in water, and the other will wash away once the print is complete. The process can be slow for some part geometries. The process is very slow if you are having typical geometries. Okay, and layer to layer adhesion can be a problem. Say if you are having a big build-up area, and the head has to move from one end to the other end, the first end will get cured and then it gets solidifies. So if you are providing a next layer, as the bottom layer already got fused, if you are pouring some material again, the adhesion, that means the attachment won't be that proper, and so it is not meant for a very big structure. Very small structures only can be built by this better method. Again, post-processing using acetone can resolve. If the problem is there and watertight is, here also it will be a porous structures. And if it is porous structure, again post-processing is required, and using acetone we can resolve this better problem. Okay. And this is the type of, here you are having material spool, and from this material spool the filament wire is coming, and from that filament wire will be fed into the heated extrusion head, and from the heated extrusion head molten material will be coming here, and this molten material will be forming on to this part of the same. So here this head will be moving, or otherwise the platform can be moved. One of the technique can be used. Okay, either the platform is moving or head is moving, one and the same. And there are different machines which are available, some of them with platform movement and some of them with head movement. So from this, the molten material forming as a layer, and once this layer is over, and again the second layer, third layer, fourth layer, like that. And suppose if you are having this overhanging, and this overhanging requires support structure. So here support structure, either you can build from the bottom to top with a very weak porous structure you will be providing in that particular case. And once the product is finished, the porous structure can be very easily cut by using edge cutters or some other machining tools. Okay. So this is the solidified model of some, just as a model I have demonstrated this. Fused deposition modeling. In fused deposition modeling, the model or part is produced by extruding small bits of material which hardens immediately to form layers. Okay, here instead of molten material, small bits we are providing, and that will be attached to the bottom layer as well as the adjacent particle also. A thermoplastic filament or metal wire that is wound on a coil is unreeled to supply the material. The same, whatever that I explained in the diagram, the same thing I am explaining here once again. The nozzle head heats the material and turns the flow on and off. I mean, suppose if we want to stop the material at some point of time, the nozzle is turned off, so that flow of material will be stopped there. And if we make it on, the flow of material will be again coming out. Typically, stepper motors or servo motors are employed to move the extruding head as well as the bed, okay, where your part is built up. Okay, so both horizontal and vertical directions. And this is this is the structure what you are having. Okay, so here you can use various polymers, including acrylonitrile. It's normally referred as ABS plastic. Okay, polycarbonate PC and polyactic acid PLA and high density polyethylene HDPE and PCABS and PPSU. Okay, these are the general polymers we'll be using. And here, if you see, this is how the structure is built. I mean, I'm showing here a continuous this thing. If you want to stop here, a gap is required, then what that I will do is I'll stop the nozzle for some time. And again, after crossing this particular thing, again, I will open the nozzle so that material will be forming here. Okay, so like that, here you can see this is one layer, and on top second layer, on top third layer, and I showed here a continuous formation, and even gaps also you can provide in between. That's not shown here. And this is the platform where I'm building up that particular thing. This platform will be moving down or up, okay, based on the particular mission. Okay, and here if you see, in between there are certain gaps. These yellow dots, they are showing nothing but the gaps are from here to here. There could be some leakage also. So that is what is called as it's not properly fused and not properly, and that mechanical strength is also not that good. Okay, so this is the thing. And okay, here let us take a 2 minutes break, and then I'll rejoin you within 2 minutes. Okay.
Okay. The link is, the attendance link is shared in the chat box. Please go through that and fill the attendance.
Satu kabanan lah. Yo. Yeah. Oh, sorry. Yeah. All of you are ready? Okay, I am starting. So here, now let us see the manufacturing process cycles. So if you want to manufacture any 3D printed product, there are 8 different techniques that you need to adapt. What are those things? Let's see. Conceptualization and CAD, that is computer aided design. Okay, so first you need to conceptualize the product, and then you have to prepare the model, and you will see all of them in detail also. And once this particular conceptualization is over and the CAD design is over, we need to convert the particular thing into what is called as an STL file. That's again a software, and the software will convert that into STL file. And once the STL file is over, this STL file need to be transferred, and manipulations of STL file on to this machine. Okay, so machine needs some adjustment. That machine setup we have to take, and then we'll go for what is called as build. So that means the machine will be start building up the particular product. Once the product is built out, then part removal and clean up. Okay, so that part will be taken out from the machine, and then it need to be cleaned up, and post processing of the part, and after that final application. So these are the 8 different processes involved in that particular thing. Okay, so the same thing what I have shown here. This is the CAD design of the particular product. That is one. And then second is the STL convert. In the STL convert, we are having certain techniques. I'll explain later. And once that is over, then file transfer to the machine. So here, the machine is having a big platform. On this big platform, you are having only very small object to be printed. That can be printed anywhere on this particular thing, and that can be given by your file transfer to the machine will decide that particular thing. And then machine setup. This machine setup, what is the temperature and what are the other things that you can give the instructions to the machine. And then after that, the billing process will be taken up. Here the billing process is going up. And once the billing process is over, we can remove the product. And after that, post-processing. Post-processing means here I'm showing as a grinding and other things can be done. And after that, your application. This being a take-up, we are enjoying with the take. Okay. And step 1, conceptualization and CAD. The first step in any product development process is to come up with some idea as to how the product will look and function. Say first, say if you want to build some item, you need to visualize that particular item, how it need to be, and what are its dimensions, and then in what way you can have that particular product, and is there any other method to get that particular product in different form. All that need to be conceptualized, and that conceptualization can take many forms, from textual and narrative descriptions to sketches and representative models. Say you are having a client, and client came and then I need this particular product in this particular shape. So he will describe the product in his terms. I mean, most of the times he will provide a sketch, or otherwise a narrative descriptions will be given by the client. And from those things, you have to prepare sketches, and from these sketches, you will be having a representative model. Okay, if this model A model is to be used, the product description must be in a form that allows a physical model to be made. Okay, if you are using additive manufacturing, then the product description must allow this particular physical model to be built up. Okay, say you are having very long overhangings, then your product is not stable and you can't build up that particular product. So you have to visualize the product, and with minimal support structures, or otherwise no overhangings or minimal overhangings. All those things you need to visualize the product before giving that particular product for the printer. It may be that AM technology, additive manufacturing technology, will not be used to realize the final product. It is not used to realize the final product. But for complex products, there are likely to be many stages in the development process where models can be used. Okay, so models can be used, and for these entered into your company. So this is your step one. And it's a design. You will be giving all the dimensions, and it will look like once the conversion to STL. Nearly every additive manufacturing technology uses the STL file format. Most of the additive manufacturing technology uses only the STL format. The term STL was derived from stereolithography. First, we have seen what is meant by stereolithography, and the STL, the abbreviation is derived from this particular thing, which was first commercial AM technology from 3D systems in the 1990s. Okay, so we almost have seen almost 30 years for this particular STL technology. Okay, considered a de facto standard, STL is a simple way of describing a CAD model in terms of its geometry alone. So here the geometry is the main thing what we'll be describing. It works by removing any construction data, modeling history, etc., and approximating the surfaces to the model of a triangle facets. So here we are building the area or the model by using what are called as small triangular structures. And the minimum size of these triangles can be set within most CAD software, and the objective is to ensure the models created do not show any obvious triangles on the surface. So, whatever your model is there, that model will be built by using these small triangles, one on the other and one beneath the other will be bridging those triangles. And as the triangles are getting attached one to the other, then the surface will be built. Okay, so and at the same time here we need to see that the triangle sharp edges should not come onto the surface, and they need to provide a smooth surface on the surface. Surface should need to be very smooth. The triangle size is in fact calculated in terms of minimum distance between the plane represented by the triangle and the surface it is supposed to represent. Okay, so this is minimum distance what is that we need to have, and how close these triangles need to be. That will say what is the surface finish that you are having, product is having. In other words, a basic rule of thumb is to ensure that minimum triangle offset is smaller than the resolution of the AM machine. Okay, so AM machine itself is having some resolution, and this offset should be smaller than the particular resolution of the AM machine, so that you will be getting a fine product. Okay, now let us go to the step 3. Transfer of this STL file to the additive manufacturing machine. Okay, once the STL file has been created, that is created by your first model, from model to STL file, and once this STL file is available, it's created, it can be sent directly to the target AM machine. Say you are having additive manufacturing machine, okay, that is 3D printer what we will normally referred as, and that 3D printer can accept this particular STL file in most of the cases. Ideally, it should be possible to press a print button and the machine should build the part straight away. This is not usually the case. Say you are having the STL file. STL file can be directly transferred to your 3D printer, and by pressing the print button, the machine can start printing the model ultimately. But this is not usually the case. Okay, and if you are doing like that, then your product quality is not that good. So for that reason, what that you need to do is you have to do certain real study before giving the print option. Okay, the first task would be to verify that the part is correct. So first you need to verify whether the product is correct, or otherwise it is having some errors in dimensions, or otherwise in the surface, or otherwise any other defects that you need to visualize on the computer screen. AM system software normally has a visualization tool that allows the user to view and manipulate the part. So that means the software which is there will allow you to visualize the product in different directions. From different directions, you can visualize the product product. And if you want to manipulate any of the thing, you can manipulate through the software. The user may wish to reposition the part or even change the orientation to allow it to be built on a specific location within the machine. Already I explained. The machine is having a large build-up area. In that large build-up area, if you are building a small sample, that sample can be kept anywhere on the specular district. That you can say in the specular district. Okay, here you can select that particular option. It is quite common to build more than one part in an A machine at a time. So if you are building up a very small model in one time, and again if you want to go for a second model, again you need to restart the machine. So instead of doing that particular thing, as a large build-up area is there, your first model can be kept at one part of the base plate, and the second model can be kept at the second part. Like that, you can place a different model on the we multiplies the same part. Suppose if you want to have the same part several numbers, all the parts can be printed at a time, thus requiring a copy function or completely different STL files. So that means you can have the same part replicas also you can have, and that option also you can select here. Linearly selected quite easily. Some applications may require a part to be slightly larger or slightly smaller than the original to account for process shrinkage or coatings, and so scaling may be required prior to building. Sometimes what will happen, you are building up one model part, and that model part as per your dimensions you have printed. So suppose sometimes what will happen, it can't fit onto some other part, so it needs to be slightly smaller or slightly larger. So you can have that slightly smaller or slightly larger manipulations can be done in this better software. And if you are having a slightly smaller than what that you can have is you can have some coating can be given, smooth coating or some other coating if you want, you can give up to that thing. Otherwise, if you want to allow some shrinkage of the material, you will be having a bigger this thing. So once the bigger coating is done, bigger product is done, it will have some shrinkage, or otherwise some filing can be done. And because of filing also, filing means smoothing the outer surface. Smoothing of the outer surface will have some shrinkage, and that shrinkage also you can accommodate in the specular process. So all that can be done in the specular process before transferring the file to your AM machine. So now the file has been, you can transfer it to the machine, but now the machine need to be set up for your application. All AM machines will have at least some setup parameters that are specific to that machine or process. So most of the 3D printers, they are having some specific for that particular machine. Suppose if you are purchasing some X person, it will have some selectable parameters, and those selectable parameters one after the other you can select. Otherwise, based on the process also you can select the parameters like temperature, otherwise the fused, the material feeding speed, all those things you can set. Some machines are only designed to run perhaps one or two different materials and with no variation in layer thickness or other build parameters. Sometimes option of two print heads. One is for one material, the other one is for other material, and one material can be fed at a faster rate and at a slower rate, or as the thickness of the material thickness can also be accommodated as per this thing. So these type of machines will have very few setup changes to make from build to build. So very small modifications can be done in this particular thing from one build to the other build. Other machines are designed to run with a variety of materials and may also have some parameters that require optimization to suit the type of part that is to be built, or permit parts to be built quicker but with a poorer layer resolution, for example. So sometimes what is that you have to have is you have to design a part. So you have designed a part and you don't know whether it suits your structure or not. So in that particular thing, if you are building up a very strengthy structure, then what will happen? Your material will get wasted, and ultimately, if it is not fitting to your requirement, then again you need to rebuild, reprint that particular thing after modifying. So in order to avoid that particular situation, what that you will be doing is you will be taking less material, and you will be building up the product with poor layer resolution. That means it is not exactly fitting the thing. It may have some, mechanical strength won't be there, or otherwise from one layer to the other layer gaps are there. All those things you are not bothered, because it's only just a model. Whether it fits in your required space, or whether it is satisfying the end customer or not, that you will be checking. So in order to check that particular thing, you will be taking a poor layer resolution. Because it takes less time to print, and as well as less material also. Less material is it's economical. That's the main reason. Such machines can have numerous setup options available. Okay, so some machines will have that particular setup options. Okay, if you are having those setup options, you have to choose those things as per your requirement. And if you are forgetting about those things, then as per the earlier settings, it will print the material, and it may not be useful for your ultimate testing. So before going to print your model, first you have to see what are the selected parameters you are having earlier, and whether those selected parameters are suitable for your present application or not. If they are not suitable, then you need to modify them, and you have, once they are modified, then you can go for the printer. Say even the temperature of the filament also is a matter of this thing. Say in cold climatic conditions, you have to go for higher temperatures, and in summer during very hot conditions, you can't go for very high temperatures. So you can choose lower temperatures, because the molten material itself will not get cooled at a rapid rate. So you have to consider that also if you want to have a good usable product. It is common in the more complex cases to have default settings or save files from previously defined setups to help speed up the machine setup process to prevent mistakes being made. Sometimes you are always going for very complex products, and whenever you are going for complex products, then what's happening is always you need to set all the options. If you are going for all the setup options, then what will happen is your time is getting wasted, and most of the times what will happen is your setup mechanism is done once, and then the same mechanism, same setup parameters are used for successful applications. Okay, normally an incorrect setup procedure will still result in a part being built. The final quality of the part may, however, be unacceptable. Say, if you are without selecting those parameters also, you can print. It's not a problem. It will print, because it's a robotic arm. If you command it, it will print, and then it will provide the product. But that particular product may not be useful for you, because it's not meeting your ultimate requirements, and it's unacceptable. Okay, so for that reasons, what is that you need to do is you have to correctly set the process parameters, and once the process parameters are correctly set, then only your product is acceptable, and it will have the required mechanical strength, or as smoothness, or as other conditions what you wanted. Okay. Step 5 is nothing but your build. The first few stages of the AIM process are semi-automated tasks that may require considerable manual control. Till now, till step 4, whatever the process you are having a manual intervention. Okay, so that means you can visualize the product by rotating it up or down or otherwise sideways, or otherwise where the product need to be printed on the platform. All those things you have to decide manually. Most of the times, a manual intervention is required till step 4. But once you are entering into step 5, no more manual intervention. Okay, semi-automated tasks, considerable manual control, interaction, and decision making. Once these steps are completed, the process switches to the computer control building phase. Okay, once the first 4 phases are over, then the computer will control the machine, and your control is only whether to exit the process or whether to continue the process. That's all, nothing else in your hands. This is where the previously mentioned layer-based manufacturing takes place. Till now, whatever the manufacturing technique that we have mentioned, that is layer by layer process is taking place, that will come into picture here. Till now, whatever the things that are there, only that's only the setup process, or otherwise the product related dimensions, etc., etc. You are fixing. Yeah? But in this build only, the actual building is taking place. But actual process is taking place. All additive manufacturing machines will have a similar sequence of layer control using a height adjustable platform, material deposition, and layer cross-section formation. Okay, almost all additive manufacturing machines will have similar sequence. Okay, maybe varying in resolution, or otherwise in sizes, or otherwise the platform may be moving up and down, or otherwise the head may be moving in X and Y directions. And those slight modifications will be there, but more or less the principle wise it will be the same. And the mission structure also I'll show you at the end. Some machines will combine the material deposition and layer information simultaneously, while others will separate them. Okay, this is the machine option, and material deposition already taking place, and layer information also will be doing sometimes. All machines will repeat the process until either the build is complete or there is no source material remaining. Say you are having source material, that means the filament is coming from a reel, and suppose if the reel is empty, then the process has to be completed, because you have not have any feed material there. Okay, raw material is not available. So in that particular case, the machine will stop. Or otherwise, the build is complete. That means your product has been finished. So once the product has been finished, your printing process is finished, and then you can take the product out of the machine. Okay. So now let's go to the step 6, removal and cleanup. Ideally, by this stage, the output of the AIM machine should be ready for use. Okay. In principle, once the product print is over, okay, then the product is ready for use. That's what we normally expect. Sometimes it's yes, but in most of the cases it's not the case. While sometimes this may be the case, more often than not, parts will still require a significant amount of manual finishing before they are ready for use. Okay, so sometimes yes, you can use them as it is, but sometimes the post-processing is required. So in all cases, the part must be either separated from a build platform on which the part was produced, or removed from excess build material surrounding the part. So sometimes what will happen is, okay, require a significant amount of manual finishing before they are ready for use. In all cases, the part must be either separated from build-up platform on which part was produced, or removed from excess build material surrounding the part. Some AIM process use additional material other than that used to make part itself. Secondary support materials will be using. Those secondary support materials will be removing. This material will be used to aid the building process in some way. Okay, support structures are used to help. Already I told you. Overhangings, if they are there, they may collapse, or otherwise they may be having warping structures. And in order to avoid them, we have to have the support structures. And once the support structures are there in the process of building up, we need to remove them by the manual process. Okay. Step 7. This is post-process. Post-processing refers to the usually manual stages of finishing the parts for application purposes. This may involve abrasive finishing. Abrasive means like your file paper or sand paper, like polishing and sandpapering or application of coatings. Okay, sometimes even for to get a smooth finish, we may paint it, or otherwise we may have some other coating what will be giving onto the product, finished product. This stage is the process is very application specific. This is very application specific because not always we require a smooth finish. Sometimes even rough finish, or otherwise some porous structures also there, they are okay. And sometimes we need a high mechanical strength. If mechanical strength is not enough, then we may do some other mechanical strength improving techniques. Some applications may only require a minimum post-processing, taking advantage of the speed at which parts are made. Other participants' applications may require very careful handling of the parts to maintain a good precision and finish. Okay, different AM processes have different results in terms of accuracy and material properties. Some processes produce relatively fragile components that may require the use of infiltration and or surface coatings to strengthen the final product. Already told you. Suppose if you want to strengthen the product, then you have to have some infiltration techniques or surface coatings we have to provide. And with that surface coating, the mechanical strength may be improved to a certain extent, not to the complete extent, but to a certain extent we can improve. This is primarily a manual task due to the complexity of the most AM products. Most of the AM products, additive manufacturing parts are very complex. So being very complex products, you can't provide a filing machine and then rotating filing machine, and then you can't just file it with mechanized filing. So you have to have a manual methods only in most of the cases because the structure itself is very complex. However, some of the tasks can benefit from the use of power tools and additional equipment like polishing tubs or drying and baking ovens, etc. Okay, so this is over. And next, let's have the last thing, that is application. Following post-processing, parts are ready for use. Okay, the parts are ready for use. Although parts may be made from similar materials to those available from other manufacturing processes like molding, casting, okay, parts may not behave according to the standard material specifications. Say you are having products from molding and casting, same product, and from additive manufacturing, that is 3D printing, you are having the same product. And both of them, they may not have the similar specifications. Okay, though the dimensions are the same, their mechanical strength, or otherwise the pore structure, or otherwise the heat taking ability, all of them, they won't be same because the process is different. Some AM processes inherently create parts with small voids or bubbles trapped inside them. Okay, there in some of the products, what will happen is some small air gaps or air bubbles will be there within the solid piece that we can't avoid, which could be the source for the part failure under mechanical stress. If the voids are more, and if you are applying mechanical stress, then the product may fail. Some process may cause the material to degrade during the build, or material not to bond, link, or crystallize in an optimum way. Sometimes what will happen is the product may not be bonded to the bottom layer, or otherwise it may not link to the adjacent this thing. Crystallization is not process proper. So in those cases, what will happen is the failure of the product will be taking place. In almost every case, the properties are anisotropic, different properties in different directions. Say you are not having the same property in X direction or in Y direction, the properties may change. Okay, this may result in parts that behave differently than if they are made using more conventional manufacturing approach. So if you are taking the conventional manufacturing approach, then this is not the case. And in all directions, the same mechanical strength or same heat processing and heat taking process will be there. Okay, that's not the case with this particular 3D printing process. Okay. Now let us see the advantage of this particular thing. Design complexity and freedom. The advent of 3D printing has been a proliferation of product. Okay, which involves levels of complexity and simply could not produce physically in any other way. Okay, very complex products can be built, and they can't be built with any other mechanical process that easily. And such products can be built by using your 3D printer. Okay, while this advantage has been taken up by the designers, mainly designers and the artists who are creating the CAD and then the STL file creation, there the main technical involvement is involved. And once that particular easily you can do it. That's not this thing. It has also made a significant import of on individual applications, whereby applications are being developed to metallize complex components that are proving to be both lighter and stronger than their predecessor. Okay, so you can have complex materials, and then you will be having light as well as the stronger materials than that. And based on your requirement, you can have light materials or stronger materials. You can create complex parts within hours. Okay, very complex products can be built within hours, and that's not the case with other manufacturing techniques. With limited only human resources in preparing the CAD file and then in creating the STL file, and after that just pressing the using the 3D printer. Okay, setting of the 3D printer. Only machine operator is needed for loading the data file and the powder materials. The finish is in your hands. During the manufacture process, no operator is required. So here operator is freed once the product is in the 3D printer. And during the particular process, the manpower requirement is not there. Okay, and 3D printing process allow for mass customization. Okay, customization is, you can personalize the products. That means, say you are having, for example, a knee joint need to be prepared, and that knee joint of one person, and because the physiology itself is varying from one person to the other person. So the knee joint, if you take knee joint of one person, can't fit into the other person. So it has to have a personalized requirement is there. So the personalized requirement can be modified in this particular case. Whereas if you are going for normal mechanical process, it is not the case. Once the product is finished, you can't have modifications within that particular thing. Whereas here, personalized modifications you can do as per your requirements. Even within the same build chamber, numerous products can be manufactured at the same time according to end users' requirements at no additional process cost. Say at the same time, we can build several products on the same platform, and that's another advantage. And here there are no tools. Say if you are going for a same knee joint, let us take. Say if you want to go for knee joint, then what is that? How they are producing? They are having what is called wax molds, or otherwise sand molds they will be preparing, and on that particular thing they will be preparing some other thing. So those are all the tools what they will be making. So those tool manufacturing is not here. It's not there in this particular process. So directly your product is coming into the picture, and there are no tools. So tool manufacturing stage is not here. For low and medium volume applications, it can be used. Okay, and can eliminate the need for tool production. Okay, and therefore the costing is less, and at the same time lead times are less. Lead times means say once the product is given to you for production and designing, and then getting the product into your hands. Okay, that lead time is very small in this particular case, and labor associated with it, and whatever the efforts we are keeping in order to develop that particular product is also less with the 3D printing. Whereas in the case of a normal mechanized process, you have to prepare the first design, then mold, and after that the other molten metal poured into that particular thing. And once the product is finished, again you need to finish it by several other methods, mechanical methods. This is an extremely attractive proposition. Okay, this is the attractive proportion as far as 3D printing is concerned. But because of the complexity advantages stated above, products and components can be designed specifically to avoid assembly requirements with intricate geometry and complex features, further eliminating the labor and cost associated with the assembly process. Suppose if you are having a ball and socket joint, say you are having here a structure and here one more structure is there, both need to be fitted. And here if you see my the internal structure is fit into this particular thing. So the gap need to be there, and at the same time my ball need to be kept in that particular thing. So if you want to take this particular thing, it is not possible with normal mechanical process. So if you are going for this 3D printing process, it can be easily, you can get that particular structure. Extreme lightweight design also it's possible with this particular this thing, and sustainable, environmental friendly, and this is energy efficient technology. Okay, and this is again a controversial thing. So sometimes they say it's energy efficiency is not there, but sometimes they say energy efficiency is there. Provide environmental efficiencies in terms of both manufacturing process itself, utilizes up to 90% standard metals, and therefore creating less waste. But it creates less waste as far as material is concerned. But at the same time, power side, it may consume more power. But also throughout an additive manufactured products operating life, by way of lighter and stronger design that imposes reduced carbon footprint compared with the traditionally manufactured products. So if you take traditional manufactured products, what will happen is carbon footprint is that. That means you will be providing a lot of heat, and then you may be using higher electrical power, or otherwise you may be using certain other metals which will be just going as a waste once a product is over. But whereas here that particular wastage is not there. No storage cost. Say if you are going for a mechanical process, your mold will be there. That mold is once the product is finished, and then if the product is delivered, that mold is a dead waste for you. Okay, and whereas in the 3D printer, that mold itself is not there, so there is no wastage of the material. And sometimes what will happen is if you want to go for some 100 pieces with mechanical process, it's not possible at the same cost. You have to go for very high production numbers in order to keep up the cost at low end. So whereas in this particular case, if you want only 1 or 2 pieces also, you can print with this particular technique, and the cost is very, very economically with this particular thing. And increases the employment opportunities because of the latest technology, and then designers and technicians which can on 3D printers can create blueprints for these products. Employment opportunities are increasing with this thing. Okay, these are all the advantages what you are having with this particular 3D printing. But at the same time, you are also having disadvantages. Okay, and this is questionable accuracy. 3D printing is primarily a prototyping technology, meaning the parts are created via the technology and mainly test parts. As with any viable test part, the dimensions have to be precise in order for engineers to get an accurate read on whether or not part is feasible or not. Okay, the 3D printers have made advances in accuracy in recent years, and the plastic metals are still having advantages. And plus or minus 0.1 mm accuracy, if it is there, then there is room for no error. Okay, but plus or minus 0.1 mm is highly critical. Most of the 3D printers are not in this particular range, but very high-end machines can give that particular precise this thing. Support material removal. Okay, and most of the support material removal is a big issue, because we have to cut each and everything, and then you have to file it, and then you have to remove the support structure in a careful manner. Otherwise, the material itself will get damaged, and again you have to reprint it. Okay, limitations of raw materials. And this is another drawback. 100 different raw materials are available, and each one is meant for only one type of application, and you can't rechange them. And all of them, they are from a specific manufacturer. Say if you are using one particular printer, the particular printer manufacturer itself will provide the raw material, so you have to take the raw material from him only. And again, the raw material recirculation can't be done that easily. So there are that concern. Considerable effort is required application design for setting up the process parameters. So in order to make a good product, process parameters need to be set. That is another drawback. And if the process parameters are not met, then the product is not, it won't meet the required specifications, and it is not meant for the final application. Material cost is also quite exorbitant, but at the same time it is coming down as people are using more and more. Okay, and material properties, tensile strength, yield strength, etc., they are still under research in most of the cases. Okay, and I will not be going into other these things because lack of time. Okay, and already this I have told you, and these are the materials what you will be using, and ceramics also we can use, paper also is used, biomaterials also there, and okay, safety features. This is one thing what you need to remember. Say as any industry is associated with some sort of pollution, associated with some sort of safety features, risk and lungs, because the powder materials, if you are using those powder materials taken by air, and then if you inhale, then lungs will get the deposits of that material, and then it may lead to some other respiratory damage, and then eye infection is another thing. Okay, so problems, it is also have problems, and sufficient care need to be taken. Risk of compressed air outlet, sometimes there will be air outlet will be there, and then dust can cause irreversible damage to sanitation, to skin contact, allergic reactions that are there, and suspected carcinogenic effects also there. Carcinogenic means cancer related problems one can get. And laser systems, if you are using laser systems, they are having some sort of problems. Okay, so here I told you that is controversial. 3D printers are energy hawks. Okay, when melting plastic with heat or lasers, 3D printers consume 50 to 100 times more electrical energy than injection molding to make an item of the same weight. Okay, so only power, it consumes more power, but at the same time less material. Okay, so unhealthy air emissions will be there. That is another thing. Okay. Okay, so here IP related problems they are there. Responsibility of manufacturers, and then weapons. If you are taking anyone can prepare a gun, and then he can use on his own without taking any license. He can prepare his own gun, as well as even bullets also he can prepare. So this sort of some problems are there even with this 3D printing. Similar to your movie piracy, here also any product can be made in your house itself if you are having a 3D printer of appropriate material. Okay, so that's the thing. And thank you. Any queries? Any queries?
Thank you, sir. Any questions from the participants for the speaker? Please unmute yourself and you can ask the question.
Okay, thank you then.
Thank you, sir. That was a very informative talk. Today, from your talk, we were introduced to a wide range of techniques, materials, and some practical applications used in 3D printing technology. Furthermore, the steps of the 3D printing process you discussed will be helpful in the future lectures in the course. Thank you once again, sir.
Thank you. And if you are using these techniques at some point of time, I'm very glad.
Yes, sir.
All the best. All the
Thank
best.
you.
Thank you very much, sir.
Thank you, ma'am. Thank you.
Now we will leave for lunch and we will assemble again at 2:15 p.m. Thank you.
Reporting the Gayatri. Network connection.